Hello friends, a very warm welcome to all of you. I hope you are all doing well. Today, our topic for the lecture is constraint motion. This is a very important topic and if learned properly, it will make the study of further chapters like Newton's laws of motion, rigid body dynamics, etc. very simple. Because all the basics are covered here. I will start from the absolute zero level that everybody can understand, no matter whatever your level is, whether you are a new 11 student or you are a dropper or you are just an university student wish to revisit the concepts and build up gradually to the level of JEE or the tougher problems. Like I will be slowly introducing the tougher problems so that you can use the basic concepts to solve them. So let's begin. So what is constraint motion? So what do you mean by the term constraint? Constraint means motion restricted by certain conditions. So what are those conditions? We have an example here. We have an object that is free to move only along the x-axis. So here is our object, and this object is being constrained by two rails or something like that. In this zone, the object is able to move only in the x direction. Or say we have a circular ring and we have a bead around it. No matter in whichever direction I am applying the force, the bead is only free to move along the circumference of the circle. Whether we put the force this side or anywhere. So this is called constraint motion. That means there is a constraint which is restricting the motion. Okay, let's begin. Actually, the types of constraint motion, these are not the standard classification, but based on the problems we encounter, I have given you three types of classifications, that is rigid body, pulley and string, and wedge and block. So we will classify the cases into these three topics. This is the classification only valid for these lectures. You won't find this in any standard books or like that. Okay, rigid body constraint. What is a rigid body? Rigid body means there should be no relative motion between the particles. That is the definition of rigid. So I have a particle here, let's say it's A, and another particle, let's say it's B. So there is no relative displacement between the particles. Suppose I displace the full rod, this rod or this object, I am displacing by a distance of 3 meters. So definitely this particle will also get displaced by 3 meters. And also this one will get displaced by 3 meters, and definitely the full rod will be displaced by 3 meters. So every particle inside this rod or inside this rigid body will be displaced by 3 meters, or the same displacement in every particle. Now suppose we have a particle here and we have another particle here, and this particle is moving with a velocity v. So what will be the velocity of this particle or any particle in the rigid body? We can say the velocity will be same for every particle inside the rigid body. Otherwise there will be relative displacement, which is not allowed in a rigid body. It doesn't happen because the body is rigid. So exactly here, that is what I have shown. So the velocity for every point, that is v or same. So exactly we will be using this property to solve the problems. You may think that this is very generic. Why are we even discussing this? I will show you why. While solving a problem, you will understand its significance. Okay, now we have a problem. In this question, we have been given a rod, that is, this rod is lying between two axes. One is x-axis I have given, and the other one is y-axis. The length of the rod is 3 meters we have two points A and B. A is the point which is touching the x-axis and B is the contact point with the y-axis. At the instant when the distance on the x-axis is √3 meter and the distance on the y-axis is 1 meter, and we have been given that velocity of A point, that is 10 meter per second square. We have to find the velocity of. Now see, from intuition we can say that if this A point will be moving this side, this B point will also come down. This is from intuition. Now let's understand something. We can develop the constraint equation, and we can also do it. We have two methods to do it. Two methods. Let's see. First of all, this rod is constantly moving, so this point A and this point B, these 2 points are shifting. Point A is moving towards this side and point B is moving towards this side. This length OA, this length, that is X, that is increasing and Y is decreasing. So this is 3 meter, this length 3 meter is constant. So we can write x square plus y square is equal to 3 square. This is from the Pythagoras theorem. This is 90 degrees, so x square plus y square is equal to 3 square. So x square plus y square is equal to 9. Now we will be differentiating with respect to t, that is time. So we have 2x here, 2x x square here. X square will be 2x into dx by dt plus 2y into dy by dt for y square. That is equal to 0 because this length is 9 and 9 meter is constant. And for in a rigid body, the length will be constant. So 2x dx by dt plus 2y dy by dt is equal to 0. Now, what is dx by dt? See, dx by dt is the rate of change of x. Dx by dt is the rate of change of x. So this x is increasing. See, this point is moving this side, so this definitely this length x, that is increasing. So we'll put here plus va. Dx by dt will be plus va, and this is our length y, and since the y point, the b point is coming closer to O, that is the origin, so we can write dy by dt is equal to minus vb because it is decreasing. So here for dy dt we have replaced minus vb equal to 0. So after rearranging we are getting vv is equal to x by y into va. Now what is x? X was √3 meter and y was 1 meter. See, the velocity of b won't be constant. A is moving at 10 meter per second, but that is constant, but vb will change according to the ratio of x and y. X is to y, x by y. So I am replacing at that instant particular when x is equal to √3 and y is equal to 1 meter. Vv is equal to √3 by 1 into 10, that is 17.32 meter. So I hope this is clear. This is a very simple method but requires a little bit mathematics. So this is method 1. Now let's see method 2. See, in the method 2, this is the rod. What we have used here is the property of the rigid body. Here the velocity of this particle will be, or this end, one end of the rod will be v. Then the velocity of every other particle will be v in the same direction. What we have found, we tried to find out, that is the velocity component along the rod, and that will be same. See, we have the velocity of point A along the x-axis va. So along the rod, this is making an angle, let's say theta, with the x-axis. So here also theta. So what will be this component? Suppose I have, this is v and this is theta. So definitely this will be v cos theta. And if this is v, this is va. So va cos theta. If this is va cos theta, every other point in this rod, every other point will be having VA cos theta velocity along the rod. Now this point is having VB, that is towards the y-axis. It is constrained to move. This point B is constrained to move along the y-axis. So what is the component of velocity of point B along the rod? That is VB sin theta. Since this is theta, this is 90 degree minus theta. So VB cos of 90 degree minus theta, that is VB sin theta. Okay, so we have VA cos theta at one point and VB sin theta at the other point. So VA cos theta will be equal to VB sin theta and VB is equal to VA by tan theta. Now what is tan theta here? Tan theta is 1 by root 3. So 1 by tan theta will be root 3 by 1, that is 17.32 meter. This is the second method. So you can use any of the methods you want, but both are equivalent. Okay. So this is the application of that concept, that every particle will have the same velocity, and velocity component along the rod or along the object will be same. So our next case will be with a string. We have a block of mass m1 and we have m2. m1 is moving with a velocity v. So what will be the velocity of m2? You will be asking, what kind of question am I asking? This is very common, that it will be v. Definitely. For the string to be kept taut, what does it mean by taut? Tight. If the string is to be tight and not loose, what do you mean by loose string? The blocks are kept at a distance which is less than that of the length of the string. So this is loose. If I am pulling this side, this won't be transferred to this block. This is block 1 and block 2. Block 2 won't, this force F won't be transferred to this block 2 unless and until the string is taut like this. So if I am pulling it this is moving with a velocity v, this also should move with a velocity v, otherwise the relative displacement will change and the string may not be taut. First of all, this v1 and this v2, v1 cannot be greater than v2, then the string will break. And this is v1, this is v2. What if v2 is greater than v1? Then this will come, this length of the string will then, the relative displacement between them will be shorter than the length of the string, so it will be loose. So exactly that is the thing we have to keep in mind, that is to keep the string tight. Exactly this is what we have to apply. Okay. Now we have a stationary pulley, that means this pulley is fixed, say on the ceiling, and we have a mass m1 and m2. Now if this mass m1 is moving downward, in which direction will the mass m2 move? Definitely upward, because this is the common sense, this is the intuition. Now if this is moving downwards with an acceleration a vector, and this is moving upward with an acceleration a2, we can write a1 is equal to a2, that is a magnitude. Both will be same. As we have already seen, the velocity should be same, otherwise the string will become loose. So definitely if we differentiate velocity with respect to time 1 times, so it will become acceleration. So, but in vector form, you just see, in vector form, a is downward and a1 is downward and a2 vector is upward, and both are of same magnitude but different direction. So we can say a1 vector is equal to minus a2 vector, or a1 plus a2 is equal to 0 vector. So this is for stationary pulley. The pulley is fixed, the pulley is not moving, and we can say a1 is equal to a2. Now let's solve this problem. We have a pulley that is stationary, that is fixed, and mass A or an object A is hanging vertically from one end of the pulley, and other end of the pulley, the string from the other end of the pulley is connected to, say, a thin something, a bead. That bead is attached to a rod. Say this is a rod, and this rod is perpendicular to the ground, and this bead is free to move only along the rod. That means only along the y-axis. Let's say this is y-axis, and let's say this is x-axis. So it is free to move only along the y-axis. Now we are asked to find Vb, the velocity of B, which direction and magnitude both, when theta is equal to 60 degree. When this theta will be 60 degree, so what will be the velocity of B? So how shall we approach this question? Here, this velocity of A is 10 meter per second. See, throughout the string, if the string has to be kept taut or tight, throughout the string, every particle of the string will be having a velocity 10 meter per second. If this is 10 meter per second, this is the 10 meter per second. Now this velocity definitely will go up. I don't think so you all need any explanation for this, why this will go up. This is common sense, intuition. If this is going down, this will go up. Although even if we assume that it will go down and we find the answer will come as negative. So there is nothing to worry if your intuition goes wrong, because mathematics will save you. Now this is Vb and this is 10. So the component of Vb along the string, say this component, this will be equal to 10. So Vb cos theta is equal to 10. So Vb will be equal to 10 by cos theta. So theta is 60 degree. So I have solved this here. Exactly the same thing I have done. So Va is going downwards and Vb is going the same. The velocity component along the string will be same, that is 10 meter per second, is Vb. So Vb cos theta is equal to 10, because this component of Vb will be taking as 10, and so we'll find the component of Vb along the string. So Vb will be 10 by cos 60 degrees at 20 meter per second. Remember one thing, the students make a very fundamental mistake here, that is they calculate this part. Up to this part they do very well, that is this is 10, so this will also be 10. Now what they do is that they do 10 cos theta is equal to Vb. That means they say that is this velocity will be transferred to this bead, but this is wrong. This is fundamentally wrong, because this bead that has a velocity Vb, this bead is having a velocity Vb, and that velocity, the component of this bead along the string, that is 10 meter per second. It is not the other way round. This is not the other way round. Now what if we have a movable pulley system? That means we have a mass m, say we have a mass m1 m2 and we have a pulley. In the previous case the pulley was fixed. Now the pulley is moving up and the displacement is xp vector, and this pulley is moving up and this pulley is moving down. So now what can we do? Okay, suppose you are sitting on the pulley. So now the pulley appears stationary to you. See, the earth is moving around the sun with a very large speed, but you don't feel that, because you are sitting on the earth and you feel that the earth is at rest. The earth is rotating around its axis, and you just calculate the linear velocity of the surface of the earth for rotation, that is r omega somehow you calculate, you find it from the internet, that is your homework, and you will be shocked to know the value, the tremendous value, but you are not aware of it, because the earth, because you are sitting on the earth, you are standing on the earth, you are lying on the earth. So when you are sitting on this pulley, just for example, the pulley is not large enough to accommodate you maybe, but if you are sitting on the pulley, then you will feel that the pulley is stationary, and then you will see this mass m1 is moving. If the mass m1 is moving up with an x, say for a distance x, this mass m2 will also move with the same distance x downwards to keep the string tight. So from the frame of reference of the pulley, exactly what we have discussed, x1 vector is equal to minus x2 vector. See, x1 vector, a1 vector is equal to minus a2 vector. Similarly, I have talked about displacement here, so x1 vector is equal to minus x2 vector. Now I can write the same thing, this x1 vector, that is with respect to the stationary pulley or with respect to the pulley. x1 vector with respect to the pulley, that is equal to minus x2 vector with respect to the pulley, because with respect to the pulley both are same. The amount of displacement here will be equal to amount of displacement here. The amount of the length the string shortens here will be equal to the amount of the string elongates here. Otherwise the string won't remain tight, but that is with respect to the pulley, with respect to, say, this line, with respect to this line. We are not interested what if this line moves or not, but with respect to this line, x1p will be equal to minus of x2p vector. Now this line is also moving, but we will not worry at all, because we have written the expression with respect to the pulley. So what is x1 velocity of mass object 1 with respect to the pulley? x1p vector, that is x1 vector minus xp vector. x2 vector minus xp vector is x2p vector, and there is a minus sign. So xp will be x1 plus x2 by 2. We take xp one side and xp vector one side, so xp vector will be x1 plus x2 by 2. And this is a very important relation, and we will be using it to solve our problems. So xp vector is x1 plus x2 vector by 2, and we have taken care of the signs here, and we will differentiate it 1 times for velocity and 2 times for acceleration. Okay, we have a problem. This is, say, A, this is B, and this is the pulley. The pulley moves up with 3 meters per second, and A moves up with 5 meters per second. Find the direction of velocity, speed and direction of B. So first of all, nothing is given, so we will assume that these are with respect to an observer standing on ground. With respect to pulley or not, that is not given, so by default it will be on ground. Now we'll simply apply our formula. Say Vp is equal to Va plus Vb by 2. See, we have not written vector sign here because everything is 1D, one dimensional, and since we have not written vector, we'll assume Vb to be in the same direction that of Va. I'll tell you why. Now what is Vp? Vp is plus 3, Va is plus 5, plus Vb by 2. If we had assumed it in the opposite direction, we had to put minus. We'll assume the positive side as plus and negative side as minus here. You can do the opposite also, but when we are not writing vector, we have to add them algebraically. When we are writing vector, that algebraic sum is automatically considered. So from here we get Vv is equal to 6 minus 5, that is 1 meter per second square. With respect to the ground, it is 1 meter per second square. Now let's see one thing. This was 3 meter per second square. This was 5 meter per second square. This is 1 meter per second square. Now let's find it with respect to the pulley. Pulley is moving up with the velocity 3. So 5 minus 3, that is 2 meter per second square upward. And this is going up 3, this is going up 1. So 1 minus 3, that is minus 2. That is 2 meter per second square downward. With respect to the pulley, P, it is the same string block system that we have studied for the stationary pulley. So the frame of reference matters here. So exactly the same thing, Vp is equal to Va plus Vb by 2, and the same thing we have done. Obtain the relation between A and B. So we have a movable pulley here and a fixed pulley here. This is the combination of the pulleys. Now we are slowly increasing the level. This is a vector, a object A, and it is moving up with a velocity Va. Now this is object B, which is moving down with a velocity Vb. Now we will obtain the relationship between Va and Vb. Okay. So let's do one thing. This is A. So let's take this point as X and this point as Y. See, we analyze for this P1. This is P1 and this is 1 and this is, let's say, X. We don't know the velocity of X, but we know the velocity of A and we know the velocity of P. So I can write here Vp1 is equal to Va plus Vx by 2. I repeat, Va is downward, so let me take downward as positive here. You can take anything, for upward also positive. It will not matter in your result. So now see, Vp1 is 0 because it's stationary, so its velocity Vp1 is 0. So this is 0 is equal to, what is Va? Va is Va, upward. What is Vx by 2? So Vx is equal to minus Va. Now let's erase this. We got Va is equal to minus Vx. This is what we'll need later. Now this is X, this is Y, and this is B, and Vb is equal to Vp2 because these two are connected, and Vp2 is Vb. So Vp2 will be equal to Vx plus Vy by 2. See, Vp2 will be Vb, Vx will be minus of Va, we have found it here, and Vy, this is connected to this part, so this is 0 because this string cannot, this point cannot move. If it moves upward, say, then this string will become like this, that is loose. So Vy is 0 by 2. So exactly the same thing I have written here, Vp1 and Vp2 we have found here. So, and see one thing, I have written here Vb as minus Vb because say upward direction was taken as positive in this case. So the same thing I have done. So upward direction is taken as positive, so Vx is equal to minus Va, and because Va was positive and Vb was taken as negative, so Vb is equal to Va by 2. So that's it. So Vb is equal to Va by 2. And in the next lecture we will be studying one more method, that is method of constant length. So that's all for today's lecture. So if you have any doubts, then please leave it in the comment section, and thank you for your patient hearing. And if you like our content, please share this video with your friends and please subscribe our channel. And thank you, and stay tuned for the next lecture.